Yeah, who's this Joff guy? Okay, first of all, how did I get roped into this? I got roped into this probably at a weak moment right before the holidays began when Deb said, hey, Joff, you want to do the first webcast of 23? And I probably had a beer in my hand or something. I went, yeah, that's a great idea. And then I'm like, oh, crap, I actually got to come up with something. So I did. And here we are. And, you know, we made it through the holidays. We made it through New Year's. Here we are, 2023. It's fantastic. Okay, here's the obligatory about me slide. I'm Joff Thyer. I work for Black Hills. I've worked for Black Hills for probably longer than most of the other people on this webcast, since about 2013. In fact, I worked for Black Hills since we were 4 people. So things have changed a lot over the years, and it's been a fun journey. I'm also an instructor for Antisyphon training courses, which is a spin-off LLC because Black Hills loves growing new companies that we have created to bring affordable training to the information security community. I highly recommend you check it out, www.antisyphontraining.com. I teach now 3 classes, although that first one's due for a massive overhaul, I will firmly admit. Enterprise attacker emulation and C2 implant development. Ooh, that's a mouthful, right? Regular expressions, your new lifestyle. If everybody wants to learn about regular expressions, by all means, take that class. It's a lot of fun. It's only a 4-hour journey, but it's super cool. And coming soon, Introduction to Python, which is one of the reasons I'm doing this webcast. So let's truck on forward and see what we got. All right, here's the scenario, right? You're performing an internal pen test. You manage to compromise a Windows application server via some sort of credential acquisition. It might be some browser you popped and you got some creds, or maybe Responder, Mimikatz, SMB relaying, whatever is going on. You manage to grab the gold and you're like, woohoo, I am logging in to the Windows application server. And, you know, maybe it's a Windows Server 2016 or something like that, or 2019. And you're in and you're like, what do I want to do now? Well, what do we all do in that situation? We want to move into post-exploitation mode, right? We want to pillage the village. Maybe we want to get some more creds. Maybe we want to do a little bit of recon. What's on this server? What file shares are there? What can we find on those file shares, et cetera, et cetera? Well, you've got a choice here, right? You can upload a whole bunch of manual tools or try to live off the land to the best of your ability. But wouldn't it be nice if you could get a C2 channel up and running? So you poke around the server and you're like, this thing has app whitelisting turned on. Isn't that irritating? And oh, look, they've got 365 Defender turned on, and maybe there's a Carbon Black or a CrowdStrike or maybe Elastic or something. So you find out pretty quickly that actually trying to drop an executable and executing it, well, it's just not going to work. Even trying some living off the land utilities might get you busted. But then, to your surprise, you're like, wait, there's a Python 3 interpreter on this server. And you go, hey, what can I do with a Python 3 interpreter? Well, it turns out you could do a lot with a Python interpreter. What I'm going to talk about today is how you can actually execute Windows shellcode with a Python interpreter. Shellcode. What is this thing we call shellcode? Well, let's not be, what I'm going to say here, let's see, naive. Let's not be naive. Sorry, the brain had to switch gears there. Shellcode is just compiled machine code, right? It is just a binary executable code. It's not a PECOF file. It's not in a loadable format, but it is just machine code that is executable by the processor. Now, one of the things that differs with shellcode is that it is written in a way that is position independent, which means it has no static memory addresses that it depends on. It doesn't have any dynamic library dependencies typically, and it can execute in memory if we can get it into the memory of the machine and point the instruction pointer of the CPU or the processor at that first address where we load that shellcode into memory. Now, shellcode or any machine code does have an architecture or flavor to it, right? x86 for 32-bit machine code, x64 for 64-bit machine code. So it's OS platform specific. It has an architecture. It is certainly not the same as an exe or a Linux ELF file or a macOS file in the case of Mac. But it can originate from almost anywhere, right? We can have shellcode that we generate out of the Metasploit project. You might have a Cobalt Strike beacon with shellcode in it. You might have, something like Brute Retell or some of these other C2 frameworks that generate shellcode. You could have even handcrafted some sort of shellcode. But the key here is how are we going to get that shellcode into memory and actually executing just by virtue of the fact that we have a Python interpreter? Well, Python 3 provides us some really good mechanisms for accessing the C language types as well as the dynamic link libraries that are part of Windows. In fact, there is a module in Python 3 called ctypes, which I literally cut from the documentation, RTFM. It actually works. It's amazing, where ctypes provides C-compatible data types and allows you to call functions in DLLs or shared libraries in Windows. ctypes also exports a couple of other objects, one of these called CDLL, and on Windows, windll and OLE DLL objects for loading dynamic link libraries. Aha! So if we have this, it is built in as part of the Python 3 installation, then perhaps we can leverage this to use the Windows 32, kernel 32 API, for example, and leverage the various function calls or the API calls in the Windows API to load shellcode. So using in ctypes, the windll object has another object called kernel 32. This allows us to actually extract function pointers for any kernel32.dll API call that we need. Now, kernel32.dll, well, it is the Windows API effectively, but kernel32.dll implements the entire Windows API with the exception of a handful of other things that are related to user32 and some other graphics related API calls. But kernel 32 is the majority of Windows. Now, underneath kernel 32 is another DLL called NTDLL, but NTDLL is not documented. Kernel 32, however, is fully documented on MSDN, the Microsoft Developer Network. So if we use this object, we can import ctypes in a Python interpreter. Then we can create a pointer to any kernel 32 API call just by referencing it out of the ctypes.windll.kernel32.function name that we're looking for object. And that then becomes an actual function pointer to the dynamic link library that we can subsequently use for our own purposes. Now, create thread happens to be an example of creating a new thread of execution in a Python process. Awesome. We might well want to use this. Just a reminder of the Windows architecture. This diagram gets thrown around a lot. It is from Microsoft. Credit to Microsoft 2006 here. The diagram is in lots of documentation on MSDN and other places. You can see here with the Windows architecture, your applications at the top layer, various DLLs related to the applications, but one of the critical DLL that exists underneath that layer is kernel 32, some services that are running, and then user 32 in the graphics device interface library. Underlying all of that layer in Windows is NTDLL, which is the runtime library that implements all of the functions, which in turn interface with the kernel in Windows. And there's this really thick line on the diagram between what we call user mode and kernel mode. And the only way you get into kernel mode when you're hacking or when you are abusing Windows systems, and it always feels good to do so. I love you, Microsoft, but it does feel good to hack some Windows systems, right? The only way you get below that line is to have privileges, right? So if you want to play in the kernel space, you need a vulnerable driver or something like that to load, and then you can play in the kernel space. But for the most part, for a generic shellcode loader or machine code loader, we're going to play in user mode space and use API calls out of kernel 32 and optionally use API calls directly out of NTDLL, which in turn will make the kernel calls that we need. Now, the challenge with using any of the API calls directly out of NTDLL is that these are not well documented. They're loosely documented by various people in the offensive security community and in communities of interest like writers of things like Wireshark for sniffing and things like that, so that people could understand some of the functions. But ntdll.dll is subject to change, and it does in fact change with newer releases of Windows. Now, from a Python perspective, one of the things that we have to do is be able to pass function arguments to these Windows API function calls. And we run into a bit of a problem here immediately. The only compatible Python objects with the C API object types are these four. The none object in Python is equivalent to a C type of null. The integer object in Python is equivalent to the C integer, so that's good. A byte object in Python, and this is Python 3 specifically. You shouldn't be using Python 2, frankly, anymore. Python 3 or die, right? Is a C type of char star, for those who are familiar a little bit with C. And then string objects is kind of like a wide character. In Python 3, string objects are actually UTF-8 encoded, and so they have to be represented as more than an 8-bit character for the C-type equivalent, because UTF-8 is actually a variable encoding scheme. Anyway, to help out, the ctypes module also defines a number of compatible C data types that we can use as functions to create a compatible type from Python at any time that we need to. In fact, there is an entire table of them. C_bool enables us to map to a Boolean type, C_char for a character type, and so on. And these are all implemented as Python functions in the ctypes module that we can use to convert data as we see fit, if and when it is necessary. Okay, I'm leading to something here, obviously. Now, one of the other things we have to do here when calling these functions, as aforementioned, is specify the required argument types to the functions. Trust me when I say it is really easy to crash the Python interpreter when you call C functions in a DLL, especially if you pass in incompatible data as a function argument to that C functions. If we specify the argument types as basically function prototypes in our script, it helps protect against the incompatible argument type problem. And it actually forces Python into a position of trying to convert the arguments that we specify into valid data types before it is passed along to the C API call inside of kernel 32, for example. So there is an argtypes attribute of any C function pointer object that we use for this prototyping. There is also a res type attribute that allows us to deliberately specify the function return type. Otherwise, it'll just default to integer. And that's not always sufficient, because some of the return types might be a Windows handle or a Boolean or something like that. So res type is also useful. Now, if you want to know what these WinAPI data types are, these are actually well documented out there. You can Google on this anytime you want. I picked a random, literally kind of a random link here. Is there a table of Windows API data types are out there? And you can see void, handle, byte, short, word, int, uint, long, bool, dword, etc. These are all the different data types and memory representation that is used for those data types if you need a reference to them. You can also find this information if you look up the actual function that you're interested in calling on MSDN, because the MSDN has a really well-documented web index essentially and web table for every single kernel 32 DLL API call, as well as user 32 and things that are above NTDLL essentially. Now, fortunately for us, the Python ctypes module also has something called wintypes, and we can import wintypes as an object into a Python script and then display, for example, all of the different data types that exist, which in turn are functions, in fact, that will enable you to convert data to this particular Windows type. And you can see a lot of the same things are represented here. Atom, bool, boolean, byte, char, et cetera, right? And I just did this inside of a Python interpreter using tab completion to illustrate these various Windows types that are actually implemented in the module. All right, so all of that is building towards me actually creating for you in a Python script an example function prototype to call directly, in this case, the create thread kernel 32 API call. So what I first do is I set up an object which I just called create thread with the same casing, the same title casing as the API call, and I set that object equal to the ctypes.windll.kernel32.create thread function pointer that exists in the ctypes module. And then I deliberately create the argtypes for the function prototyping for create thread to match effectively what's on MSDN, right? So I use an LP void, which is called long pointer void. I use a C_size t, which is very similar to an integer. I use another LP void, a double word, an LP void, etc. Now, astute people will point out by looking at the slide that the MSDN compatible function call that is documented, the argument types do not match exactly the ones that I used. For example, the very first argument has LP security underscore attributes instead of LP void. If you do a little bit of research, you very quickly find out that a long pointer void is exactly the same actual object, if you like, as LP security attributes is. In fact, they're analogous in the Windows Developer Kit header files. And so, there's a little bit of magic in there, if you like, or I'd say extra research on Joff's behalf. An LP void is equivalent to that. An LP void is also equivalent to LP thread underscore start routine. And it's okay to use them in the way that I have. Okay, so we function prototyped here. Very good, all right? What about shellcode execution using the Windows API? For those of you that have done plenty of pen testing, have probably often had to develop loaders in C# or maybe develop loaders in C and stumble your way through some code for evasion of EDR, XDR, antivirus, Windows Defender. My God, Microsoft Defender has gotten so much better over time that it is, in fact, a defense we have to evade as well. There are many techniques to consider for shellcode execution. Remote process injection is something that we probably want to shy away from these days because it is often detected by EDR, XDR solutions, right? For our purposes, if we create a thread within the Python process itself, Windows is probably really not going to notice that. And most of these defensive solutions are not likely to notice. There's no guarantees, right? But they're not likely to notice either. So to create a thread in the same process, well, there's basically 4 steps here. It's relatively simple. We have to allocate some virtual memory in the process. We have to copy the shellcode to that allocated memory. Then we have to create a thread of execution with the starting address of the allocated memory set for that create thread API call to where the shellcode is in memory. And then we just wait on the thread to terminate. And sometimes the thread terminates immediately. Let's say if it's just a command execution, like popping a calculator, which is what I'm going to demo. Or sometimes the thread does not terminate if, let's say, it's a full-blown C2 channel that's reaching out to the network, reaching back to Cobalt Strike, reaching back to Metasploit, whatever it might be, right? So we probably need the Python process. In fact, not probably, we do need the Python process to stay alive if the thread blocks and sits there executing, let's say, our C2 channel for some period of time. If the Python process dies, then the C2 thread would die with it, and that would, of course, would be suboptimal. Now, before I go down that path, there are a myriad of ways you can get busted. And, today, modern defenses are extremely good, right? Sandbox execution. I'm not going to show you an implementation of this. I'm really just pointing out the ways that you can get busted. There are ways to implement code to do this. I'll leave that for your own research. But you can avoid sandbox execution in some cases by just checking the time zone on the system of choice and or perhaps the number of CPU cores. If it's less than 2 or 3 CPU cores and the time zone is set to UTC, it's probably a sandbox. Bail out of the process. Don't do anything. If the entropy score on the artifact is too high, you will often get a static analysis that will flag your artifact and delete it immediately. So lower the entropy. Put lots of English words in the script or in the source code. Put a lot of null characters in there. The entropy will be lowered and your artifact will pass by the entropy score check. If you allocate read, write, execute virtual memory segment in the remote process, that is a pretty much giveaway tell to any EDR that's looking at event tracing or kernel notification callbacks that you're likely doing shellcode injection. So don't allocate read, write, X. Allocate read, write first, then change it to read, execute, for example. If you're able to, and you've got kernel access, disable event tracing, kill those kernel notification callbacks. You can actually blind the EDR. That's a much more advanced topic that I'm going to teach today, of course. Specific API call hooking in NTDLL in user mode. You can evade this by using things like syswhispers for C-based projects where you can compile in direct kernel calls and avoid any of the NTDLL API hooking that might be going on. I will tell you that NTDLL API hooking, while it's still there, is probably less favored as looking at things from a kernel notification perspective these days, from the defensive perspective. Static analysis match on shellcode. This is easy. You have no excuse if you just dump plain text shellcode from Metasploit or something like that into your binary and complain about it getting busted. Encrypt it. Okay, encrypt it. And I'll show you some ways to do that as well. And then lately, memory scanners are getting much more efficient at looking for virtual memory allocation that is not backed by a disk image. Elastic EDR is particularly good at this. Some suggestions maybe. Use a heap, an executable heap for the shellcode execution. Maybe make the new thread base address look legitimate. There's a technique out there, and you can do a little research on this for later. This is not in the Python context directly, but there's a technique out there where you could perhaps load a legitimate function out of kernel 32, set the base address of the thread to that function, then suspend the thread, do a context switch, and then set the address back to your shellcode. And then from the memory allocation perspective, the scanner thinks you're calling a legitimate function, right? So there's ways to kind of get around that stuff. Machine architecture does matter. You are going to be creating a local thread in Python 3. If the Python 3 process is a 64-bit interpreter, then the shellcode has got to be 64-bit. These things must match. If you're creating thread in a remote process, then you must look at the architecture of that remote process and determine whether it's a 64-bit or 32-bit process. Now, less and less this is a concern because we are living now in a world where almost everything we encounter is a 64-bit architecture today. But you may encounter some older networks. Maybe you're working in the infrastructure space where you're looking at industrial control systems where you have to deal with much older, let's say Windows XP embedded controllers or something like that. And you're dealing with 32-bit systems. So we cannot ignore architecture altogether. But on that note, just a cautionary warning, if you are dealing with industrial control systems and 32-bit unpatched Windows XP Service Pack 0, you probably don't want to touch it from a shellcode execution perspective because your thing will probably fall over dead and you could get in big trouble. On the screen, there is a screenshot of me in Python using a couple of Python statements to determine whether I have a 64-bit or a 32-bit Python interpreter. sys.maxSize in Python contains the maximum integer value, which is going to be 2 to the power of 64 minus 1 or 2 to the power of 32 minus 1. I meant to say 31 there. Sorry. 2 to the power of 31 minus 1. So for either a 64-bit or 32-bit system, you could compare that value. And if it is equal to 2 to the power of 63 minus 1, for example, then you are on a 64-bit system because the integer is very big. The word size is very big. Alternatively, you can use the platform module and look at the architecture function in the platform module, and it'll actually tell you 64-bit and the target operating system that Python interpreter is running on.